audible? My
Yes,
screen is
sir.
visible? Okay, so good evening everyone and welcome for the third live session for the NPTEL course Introduction to Semiconductor Devices. As you know, it is being taught by Professor N.K. Emani from IIT Hyderabad, and I am your official PMRF TA for conducting these live sessions. And I am a PhD scholar at IIT Madras. I work in CMS experiment at Large Hadron Collider, Geneva. Okay, so that's it about myself, and let's get started. So as you all know by now that the plans for these sessions from my side is as follows. So briefly, for the first 10 or 15 minutes, I'll briefly discuss the uh, contents discussed in the regular lectures for the current week. It will be a quick recap of the topics covered so that you will have a quick refresher, so that the problems that we'll be solving in the next part of the session will be easier for you to understand. Then we'll move to our main content, that is solving the assignment problems, which are primarily from the previous courses offerings, and also I have included some of the competitive exams questions such as GATE exams questions, which are related to this week's lecture content, so you can get feel that what you are learning is actually important in these competitive exams as well. And needless to say, you are here for an interactive session, so feel free to stop me at any time and ask me any question if you have any doubt. Okay, so till now, can you hear me well? You can see my screen. Just confirm. Can anyone just confirm?
Yes, sir.
Okay, so okay, let's start with the review for this week's lecture content. So first of all, the week started with an important phenomena of carrier transportation, that is drift and diffusion. So we in the last week, actually not in this current week, we considered the semiconductor in equilibrium, and we determined the electron and hole concentrations in the conduction and valence bands. So knowledge of densities of these charged particles, like the carrier densities, is important towards an understanding of the electrical properties of our semiconductor material. The net flow of electrons and holes in a semiconductor will generate currents, and the process by which these charged particles move is called the transport. So in this week, we basically try to cover two important transport mechanisms in the semiconductor crystals. First is the drift movement of charges, which is because of the electric field. So the drift is the movement of charges due to an applied electric field. And then we moved on to the second mechanism, the diffusion, that is the flow of charges due to the density gradients, the carrier density gradient inside the semiconductor crystal. So because of that gradient being present, there is net movement of charges from the region of higher concentration to the region of lower concentration. So that is the density gradient giving rise to the diffusion, which is a second transport phenomena. So if you just consider a simple physics example, in which a container, say, uh, let's say a container, just a minute, let's say a container which has a membrane present in between, and one part of the container has a lot of gas molecules, you can say, and so the container is divided into two parts by a membrane, and the left side, as you can see, is containing the gas molecules at a particular temperature, and the right side is initially empty. The gas molecules are in continual random thermal motion, so that when the membrane is broken, the gas molecules flow into the right side of the container. So the movement from the higher concentration region to the lower concentration region is happening, and the diffusion is the process which actually took place. And if the gas molecules were electrically charged, if you consider, the net flow of the charges would result in the diffusion current. Okay, so this is to tell you the diffusion in a simple gas molecule in the container with membrane. We also talked about the carrier diffusion coefficients. So our our diffusion current density for say electron, if you consider, is directly proportional to the density gradient, so dn by dx, and is also proportional to the charge. Similarly, for the whole density gradient, whole density charge density, Jp diffusion is also proportional to the charge gradient, dp by dx. We are considering one dimension, and also to the charge, and the proportionality constant in these two equations is called as the diffusion coefficient. So electron diffusion coefficient in the electron case, that is dn, and the whole diffusion coefficient dp in the holes case. So its unit is centimeter square per second. So you need to have a look at the units as well, so that in the problems you'll understand how can these be helpful. Also, we talked about, yes, one more important point here is that the diffusion of holes from a region of high concentration to a region of low concentration produces a flux of holes in the negative x direction. And since the holes are positively charged particles, the conventional diffusion current density is also in the negative x direction, and hence you can see a negative sign here. So the total current density one can write, which is the sum of the drift current density and the diffusion current density. So this is drift and this is due to diffusion. Okay, we also saw the how the effect of non-uniform impurity doping concentration in a semiconductor material. So when a semiconductor material is uniformly doped, there is no gradient present, but when there is, in ideal case, that is the true, but in reality there is no thing called as the uniform doping. There is always some non-uniformity present, and owing to that non-uniformity we get effects in the semiconductor material. These are called as so-called induced electric field because of non-uniformity in the impurity doping. So the total current density you can see here. Let us move to one simple problem directly. I have included that problem to uh, make you aware about the significance of diffusion. So how diffusion plays a key role in the semiconductor, how it is significant. So I'll read the problem for you. The objective of the problem is following. We calculate the diffusion current density given the density gradient. So we are given an n-type gallium arsenide semiconductor whose temperature is given as 300 Kelvin. The electron concentration varies linearly from 10 to the power 18 to 7 into 10 to the power 17 per centimeter cube over a distance of 0.1 centimeter. Calculate the diffusion current density if the electron diffusion coefficient is dn is equal to 225 centimeter square per second. So we know the diffusion equation, like diffusion equation Jn, diffusion for electron we are considering here. It is E times the charge of the electron times the diffusion coefficient times the gradient of charge present. So as you can see, these changes in the density and also the distance is quite small, so we can approximate it to E times dn delta n over delta x. Okay, so just putting the values, so we'll have the electronic charge given as 1.6 into 10 to the power minus 19 coulomb times the dn, which is given as 225 centimeter square per second. Now delta n, that is the change in the density with distance, is given as 1 into 10 to the power 18 minus 7 into 10 to the power 17. This is per centimeter cube over a distance of 0.1 centimeter. Okay, so this is just an elementary calculation. If you calculate this, you will get the diffusion current density J, and diffusion for our semiconductor at 300 Kelvin is 108 amperes per centimeter square, sorry. Okay, so one important point I wanted to mention here is that you can see a significant amount of diffusion current density being produced by just a merely a small density gradient being present. So a significant diffusion current density can be generated in a semiconductor material with only a modest density gradient. So you can see the value of the density gradient because of a small amount of uh, density current because of small amount of density gradient that is introduced. Now let's go to our review. So we'll continue with our review. This is, I think, the second slide for the quick review. We then moved on to an important concept of non-equilibrium excess carriers inside the semiconductors. So what we basically did was, okay, so excess electrons in the conduction band and excess holes in the valence band may exist in addition to the thermal equilibrium concentrations if an external excitation is applied to the semiconductor. So we are considering an external stimulus, and in this particular point, we actually professor discussed the behavior of non-equilibrium electron and hole concentrations, which is as a function of time and space coordinates. So the excess electrons and excess holes that are produced or generated because of an external excitation do not move independently of each other, and these excess carriers diffuse, drift, and recombine with the same effective diffusion coefficient, drift mobility, and lifetime. And this actually the phenomenon of ambipolar transport. So the excess carrier, these are produced because of the external excitation, actually dominate the electrical properties of a semiconductor. And also the behavior of excess carriers in this respect is quite fundamental to the operation of semiconductor devices. So that's why this is quite an important point. So let us consider electrons in the valence band may be excited into the conduction band when, for example, high energy photons are incident on a semiconductor. And when this happens, not only is an electron created in the conduction band, but a hole is also created in the valence band. Thus, an excess than electron hole pair is generated, and the additional electrons and the holes that are called as the excess electrons and excess holes. The excess electrons and holes are generated by an external force at a particular rate, and let us consider this rate to be as shown here. This rate is Gn prime and Gp prime. This is the excess electron and hole generation rates. And important point to note here is that these rates are actually equal, because for the direct band-to-band generation, the excess electrons and holes are also created in pairs. So we must have Gn prime, that is Gn prime is equal to Gp prime. So the rates of electron and hole production is equal because they are produced in pairs. Also other parameters are also summarized in this particular table, as you can see. Then we saw also the minority carrier dynamics, such as the minority carrier diffusion equation, and then we moved on to an important concept of quasi-Fermi energy levels. So let me just before that, let me write down for the excess electron and hole created the concentration of electrons. Okay, so the concentration of electrons will be n naught plus delta n. So the concentration will be n, just a moment. Okay, so the total concentration we can write n is equal to n naught plus delta n. Similarly for holes it is p naught plus delta p. Okay, p. And when n naught where n naught and p naught are the thermal equilibrium concentrations and delta n and delta p are the excess electron and hole concentrations. So the external force has perturbed the equilibrium condition so that the semiconductor is no longer in the thermal equilibrium, and from these two equations we can in the non-equilibrium condition we can write one important relation, that is n times p, which is not equal to the Ni square, which is equal to n naught p naught. So this is also an important relation for a non-equilibrium condition. Then as I told you that we moved to the quasi Fermi energy levels. So as we know that in the thermal equilibrium, electron and hole concentrations are functions of the Fermi energy, and we can write our the electron and hole concentrations as n naught is equal to Ni times exponential of EF minus EFI by kT, and similarly for the holes it is EFI minus EF by kT, where EF is the Fermi level, EFI is the intrinsic Fermi level, the position, the level of Fermi energy at the intrinsic condition. So these are the electron and hole concentrations when there is a thermal equilibrium. Okay, Ni is the intrinsic carrier concentration. Now, if excess carriers are created in the semiconductor as we saw in the non-equilibrium condition, we are no longer in the thermal equilibrium and the Fermi energy is strictly no longer defined. However, we may define a quasi-Fermi level for electrons and a quasi-Fermi level for holes that apply for non-equilibrium condition. So if you consider delta n and delta p as our excess electron and excess hole concentrations respectively, then we may write our carrier equations in terms of the quasi-Fermi levels as, okay, I'll write it where I can write, okay, I'll write it here, n naught plus delta n will be equal to Ni times exponential of EFn minus EFi minus EFi over kT. And similarly for the holes, that is P naught plus delta P is equal to Ni exponential of EFi minus EFP over kT, where we have introduced the concept of quasi-Fermi levels, wherein EFn and EFP are the quasi-Fermi energy levels for electrons and holes respectively, and the total electron concentration and the total hole concentrations now are the functions of these quasi-Fermi levels. So EFn and EFP are actually the quasi-Fermi levels. Okay, so let's move to the short summary. Okay, so in the week short summary, I have following points to make. First of all, it is we consider the interpretation of energy band diagram. So when an electric field exists inside a material or applied as an external stimuli for the non-equilibrium condition, the band energy is like EC for the conduction band and EV for the valence band become a function of position, and the resulting variation of these particular energy levels like EC and EV with position on band diagram is popularly called as the bond bending, and it actually serves as a powerful tool for interpreting different parameters such as electrical potential, electrical field and energy, etc. So of particular significance is this particular equation wherein the electric field as a function of variation of these energy levels is shown. So electric field is given as dEc by dx, 1 over charge. Similarly for the valence level as well as the intrinsic level. Then we go to the second point, which is the minority carrier diffusion equation. So as we discussed earlier, that diffusion is a migration of carriers because of the presence of the density gradient from the region of higher density to the region of lower concentration. And the minority carrier diffusion equation is actually a partial differential equation in space and time coordinates, which depicts the evolution of carrier action when a semiconductor system is perturbed. So there are some assumptions that we make while deriving the minority carrier diffusion equation, that the system is one dimensional, we are only considering the minority carriers, the electric field is zero inside the semiconductor, and the perturbation is primarily because of the photo generation of the carriers. Okay, and also we impose the low level injection condition. Okay, let us move to the third point. Okay, so those minority carrier diffusion equations are for the p-type and n-type material are summarized here for your reference. This equation seems quite complicated at the moment, but we can reduce its complexity by applying different simplifications, which depends upon the given problem. Also, we saw an important parameter called as the minority carrier diffusion lengths. So basically, it is defined as the length wherein the excess carrier concentration falls off exponentially to 1 over E value. 1 over ETH value uh, to that at the point of injection. So it is defined in terms of minority, it is defined as the minority carrier diffusion length, and you can see the minority carrier diffusion lengths for the hole case and for the electron case. Okay, so in short, these diffusion lengths is the average distance a hole or electron diffuses before it recombines. So this is also important point to note while considering the minority carrier diffusion lengths. Let us move to the final point. Okay, so as we discussed in the quick review also, that quasi Fermi levels are the Fermi levels which are considered in the non-equilibrium condition because of the perturbation, and by definition they are related to the non-equilibrium carrier concentrations in the same way as the Fermi level is related to the equilibrium concentrations. So EFN and EFP are given as the quasi Fermi levels for the electron and hole case respectively. Okay, so I think this is quite a good summary, and we should now move to the assignment problems. So the problem, okay, so first problem we saw on the diffusion current density. Now let us move to the problem number 2 and 3. So for the problem number 2 and 3 we have common data given. So this is the common data, I'll read out for you. A silicon sample is maintained at say 300 Kelvin, and it is characterized by the following energy band diagram, where EF is we can consider the reference energy level. So let us move to the problem 2. Okay, it is asking that referring to our figure 1, that is referring to this figure, sketch the electric field inside the silicon semiconductor as a function of x, that is the distance. So what we have asked is the electric field versus the distance x given this particular band diagram. So for this simply we can go to our summary page where we have written a important equation. As you can see here, our electric field is given as a function of the variation of our energy levels with respect to distance. So electric field is given as 1 over q dEc by dx, 1 over q dEv by dx, and 1 over q dEi by dx. So by looking at this particular equation, you can see that the energy with respect to the position can be calculated quite can be determined quite straightforwardly, and you can see that the slope that is given by dEc by dx, dEv by dx, and dEi by dx is actually constant in all these three in all the three cases, and this is essentially our electric field, which is proportional to the slope. So as the slopes are constant, you can see from the options that option A is best describes our variation of electric field with distance. So because of the constant slope, you can say our electric field remains almost constant as a function of distance. So the answer is option A. Is it clear? Do you have any doubt in this?
No, sir.
Okay, I take it as no, and I'll move to the question number 3 then. Okay, so it is also based on the figure number 1. So the sketch of kinetic energy of electrons and holes inside the silicon as a function of x is best depicted by. So in the previous problem we were asked to find the electric field versus distance. Now we are asked here to find out the kinetic energy variation as a function of distance. Okay, so looking at the band diagram, we can write, so this is our, you consider this is our EC, our reference level is here EF, and our EV is this, it is going further. Now the kinetic energy of electrons is basically the difference between uh, distance from the EC from the electrons. So this is our actually the kinetic energy for the electrons. Similarly, the kinetic energy for the holes is actually distance from EV. So the kinetic energy for the holes case is this, kinetic energy for the holes. So as you can see from the figure here that as the uh, as the distance increases, so this is increasing distance, as the distance increases, the value of kinetic energy for electron, which is actually the difference between the EC value and the AF, goes on decreasing, and for the whole case it is a reverse, that is the kinetic energy goes on increasing. As you can see, the difference is getting increased with distance. So okay, so what do you guys think is the correct option for this? Can I have a couple of answers for this? This is just a simple thing. What do you think is the correct option? I have described the kinetic energy inside the uh, band diagrams. Can I have one answer?
C option.
Okay, good. Okay, so people are saying C option, and Indeed, that is the correct option. So we can see that the kinetic energy for electron case is decreasing with the distance, and for the hole case it is actually increasing. So option C. Now let us move to problem number 4. This problem I have taken from the GATE previous GATE exams. This appeared for GATE 2014 for EC. Okay, the question is as following. Assume electronic charge Q is equal to 1.6 times 10 to the power 19 coulomb, kT by Q given as 25 millivolt, and electron mobility is also given. So these are some parameters that are given. If the concentration gradient of electrons injected into a p-type silicon sample is 10 to the power 21 centimeter cube, so the concentration gradient is given, the magnitude of the electron diffusion current density. Now we also saw one problem of the diffusion current density, but this is a different problem and different way of solving this problem. So let me okay, so let us solve this problem. Now the whole the mobility is given, and also the concentration gradient is uh, given. Remember that the concentration gradients, this is wrong, it has to be centimeter to the power 4. Okay, so we know that one thing, that the diffusion coefficient, in our case the electron diffusion coefficient, has the unit of centimeter square per second. Okay, and our diffusion density that we need to calculate it is in ampere per centimeter square. So the diffusion density is given as charge times the diffusion coefficient times the gradient. So the gradient is given, charge is given. Now let us calculate the diffusion coefficient first. The diffusion coefficient is indeed calculated as following. Diffusion coefficient is basically the product of mobility times the kT by Q parameter. So from dimensional analysis also you can see the mobility is given as centimeter square plus centimeter square by whole second, voltage times second, and our kT by Q is in millivolt. So we can cancel this, it will form in the centimeter square per second. So we can calculate the diffusion coefficient first. So diffusion coefficient, mobility given as 1000 centimeter square per volt second times our kT by Q value, that is 25 millivolt, 20 power minus 3 millivolt. So we'll have our diffusion coefficient given as 25 centimeter square per second. So now you can substitute these three values in the diffusion current density Jn, which is given as 1.6 times 10 to the power minus 19 for the charge, times the diffusion coefficient, in our case it is 25 centimeter square per second, and the gradient given as 10 to the power 21 per centimeter cube. Okay, so if you just calculate it, we roughly get it as 4400 and 4144 amperes per centimeter square. So the closest answer to this thing is 4000. So the diffusion current density in ampere per second square for this problem is 4000 ampere per centimeter square. Okay, is it clear? Else we'll move to our next problem, that is problem number 5. So this is a problem that you can recall from our quick review, that the question is, for a p-type semiconductor, the minority carrier diffusion length is given by. So the minority carrier diffusion length is asked for a p-type semiconductor. So okay, so let me just give a couple of hints for you. We have given a p-type semiconductor. That means our majority carriers are holes, and our minority carriers are electrons. Okay, so we need to calculate the minority carrier diffusion length, and in for the electron we have the minority carriers. For this case we have the minority carriers as electrons. So the diffusion length should have diffusion coefficient as dn for electron, and the time characteristic time tau n. So we have two options here. This is one option and this is another option. So let us do a dimensional analysis and see which of the options for our case is correct. So we know that diffusion length in let's say it is in centimeter, has to be in centimeter, and we know that our diffusion coefficient has the unit of centimeter square per second, and our tau n is in seconds. So for the option A we have dimensions as centimeter square per second times second. Second gets cancelled and we have centimeter, and for this case we have centimeter square per second times second, so it goes to centimeter per second. So it is not a correct option, and option A is the correct option. So for a p-type semiconductor, the minority carrier diffusion length is given by under root of dn times tau n, where dn is the diffusion coefficient and tau n is the characteristic time. Okay, I hope this is clear, and let's move to the next problem. Okay, so this is also a common data problem. So this is this data is given for problems 6 to 9. I'll read out the problem for you. Consider a bar of p-type semiconductor, p-type silicon, that is uniformly doped to value of doping given as 2 into 10 to the power 16 per centimeter cube, and the temperature is given as 300 Kelvin. The applied electric field is 0, so we are only considering an external stimuli. Light is incident on the end of the semiconductor as shown in the figure. The steady state concentration of excess carriers is also given. So delta P0 and delta N0, which are the steady state concentrations, which is given as 2 times 10 to the power 14 per centimeter cube. And here we need to assume that the following parameters are applicable for this case. Okay, so let us move to problem number 6, which is based on this particular information. Okay, so the problem is as following. What is the steady state electron and hole concentrations at x is equal to 0? This is what they have asked. So we know that the steady state concentrations are given as n is equal to m naught plus delta n naught, and p is equal to p naught plus delta p naught. Also we have given the value of p naught, and that value is 2 times 10 to the power 16 per centimeter cube, but n naught is not given, so we need to calculate n naught, and we know a simple relation for the steady state is that n naught times p naught is actually equal to ni square. So we can determine n naught from here, and that is ni square divided by p naught. Okay, so ni is the intrinsic carrier concentration. If you substitute the values, ni is 10 to the power 10, so you can get the value of n naught as equal to 5 times 10 to the power 3 per centimeter cube. So we have N naught, we have P naught. The values of delta N naught and delta P naught are also given. Delta N naught and delta P naught are same, but you can see that the value of P naught is quite higher than the value of N naught, and hence we get the values of N naught and P naught as, if you just substitute these values, you will get N is equal to 2 times 10 to the power 14 per centimeter cube, and P is equal to 2.02 times 10 to the power 16 per centimeter cube. So the option D is the correct option for the steady state electron and hole concentrations at x is equal to 0. Moving on to problem number 7, which is also based on the previous data that we summarized. Calculate the minority carrier diffusion constant in the unit of centimeters. Okay, I think this is also wrong. The unit has to be centimeter square per second, as we saw numerous times that the diffusion constant is given in the centimeter square per second unit, and length we have to determine in the micrometer. Okay, so for this also, uh, just a moment. Okay, as we saw that the diffusion coefficient is given in terms of centimeter square per second. So again, we can use some dimensional analysis and try to solve this problem. Mobility is given in terms of centimeter square per volt second. So to calculate the diffusion coefficient, we'll have to use mobility times the value of kT by Q. So mobility is given as uh, 1200, and the temperature is given as 300 Kelvin. So if you can include the values of these parameters, 1200 times, if you calculate kT by Q by substituting the Boltzmann constant, the charge value and the temperature, you will get it as 0.0259. So we'll have the value of diffusion coefficient dN, which is equal to 31 times 31.2 centimeter square per second. So this is the value. Now let us calculate the diffusion length as well. So we know that the diffusion length is given as ln is equal to under root dn tau n. Okay, so the value of diffusion coefficient we calculated, it is 31.2, and the tau n, which is the time constant, given as 10 to the power minus 6 seconds for electron. So we can put on that value, and in terms of micrometer, if you just calculate it, you will get ln is equal to 55.85 micrometer. Okay, so the option, because our minority carriers are electron, option is this, that is dn is equal to 31.2 centimeters square per second, and ln is equal to 55.85 micrometers. Okay, so let's move to the 8th problem, which is also based on the parameters we have specified in this particular slide. So the problem is as following. The electron concentration at x is equal to 30 micrometer is asked. So we know that the relation for the electron concentration as a function of position is nothing but n of x is equal to n of n at the 0x times exponential of minus x over ln. So this is an important relation to keep in mind. So we can calculate or determine the electronic concentration at any position x given the initial value at x is equal to 0 and the diffusion length ln. So in our case, if you can just substitute the values of n naught is I think 2 to the power 10 to the power 14, yeah, 2 times 10 to the power 14. Okay, so at x is equal to 0 we calculated it. So if you can substitute its value, 2 times 10 to the power 14 exponential of minus x is at 30 micron, and we calculated in the last problem the diffusion length is as given as 55.85 micron. So if you can just substitute that value, you will finally get the value of our electronic concentration at, this is at x is equal to 30 micron, and it is given as 1.17 times 10 to the power 14 per centimeter cube. So the answer for this is option A. The electronic concentration at x is equal to 30 micron given as 1.17 times 10 to the power 14. Okay, so let's move to the last problem, which is based on this particular data. That problem is as follows. The electron diffusion current Jn at x is equal to 30 micron is asked. Okay, so we also know the formula for this is the electron diffusion current Jn, which is given as the charge, electronic charge, times the diffusion current, diffusion coefficient, times the gradient, that is dn by dx. Okay, now we know the charge, we can just substitute the value. It comes out to be 1.6 times 10 to the power minus 19. We calculated the value of diffusion coefficient dn as 31.2 centimeter square per second, 31.2 centimeter square per second, and we can substitute the gradient value as well, and gradient value can, so dn by dx can be approximated as now delta n by delta x. Okay, and at 30 micron, so let us forward, that is n at x is equal to 30 micron minus n at x is equal to 0 micron divided by x. Okay, that is our uh, change in x, that is delta x. So this is actually the parameter value for the dn by dx. So we can substitute the values of this. We calculated in the previous example here. N of x at 30 micron is given by 1.17 times 10 to the power 14. So 1.17 times 10 to the power 14 minus the value of the concentration at x is equal to 0, which is, I'm sorry, just a moment, I think something is fishy here. I see. Actually, the concentration is decreasing. So the concentration at, we should write it otherwise, that is 2 times 10 to the power 14. This is the concentration given at x is equal to 0 and times x, which is 30 micron. So if you just substitute the value of dn by dx in this particular equation, you will get the value of Jn, which is the electronic diffusion current, as minus 0.138 ampere per centimeter square. One important point to note here is that this negative sign. So this actually indicates the current direction, and it tells us that the current direction is opposite to the diffusion of the electrons, and hence our correct option for the electronic diffusion current at x is equal to 30 micron is minus point minus 1 point minus 0.138 ampere per centimeter square. So the option C is the correct answer. Okay, so I think with this we can move to our last problem, which is independent problem. It is not based on any data. So the problem is as follows. If the quasi-Fermi level splitting is given as 10 times the kT, what is the value of n times p? So what we have given is EFN minus EFP is given, and we are asked to find out the NP. So we can remind from the quasi-Fermi level equation. If I just go to the summary page where I had written them down here. So these are the equations for the quasi-Fermi level for electron and quasi-Fermi level for hole. So let me just write it here only. Our EFN minus EFP is nothing but EI. If you just call this as equation A, equation B, we can just subtract equation A from equation B. So LHS is simple. Now let us do the same thing in the RHS, that EI minus EI times KT ln of n over Ni, and minus times minus becomes plus. So we have KT ln P over Ni. Okay, so if we just simplify it further, this cancels. KT we can take as constant outside the bracket, and so we have ln of n over Ni plus ln of P over Ni. Okay, so we know that ln of x plus ln of y is equal to ln of xy. So this is an elementary concept to remember. So this actually becomes KT times ln of np over Ni square. np over. So EFN minus EFP becomes KT times ln of np over Ni square. Okay, so let's substitute the value of EFN minus EFP here. Sorry, that is 10 times KT is equal to KT ln of np over Ni squared. We can cut this. Let us do the exponential on both sides. Exponential of 10 is equal to exponential to the power ln goes to 1. It will have np times Ni squared. Therefore, the value of n times p, that is our parameter to be determined, np is nothing but e to the power 10 Ni squared. That is option C. Is it clear? Is there any doubt in this? Hello, can I have a couple of yes or no? Okay.
Yes, sir. Clear, sir.
Is it clear now?
Yes,
Yes,
sir.
sir.
Clear, sir.
Okay, thank you. So the problems are over, but we have a couple of more minutes, I guess. So we can move to one more question. Okay, so going to the last problem. The energy band diagram is given. So this problem appeared in the EC Gate 2021. The energy band diagram for a p-type semiconductor of bar of length L is given. This is the equilibrium condition, and the valence band EV is sloped since doping is non-uniform. So we saw the condition of band bending, and the difference between the energy levels of the valence band at the two edges is given as delta. So this is the delta value. So we know that what we have asked is the magnitude of electric field developed inside the semiconductor bar. So we need to calculate semiconductor, the electric field developed, but we know from our equation 3 that the electric field developed is given as a function of the changing the band levels, the EC, EV and EI with respect to position dx. So in our case, the band that is bending is the EV, that is valence band level. So we can write E as equal to 1 over q dEV by dx. Okay, sometimes the problem appears little daunting, but the solution is not as daunting. So we can see from the data given is that the change in energy, the change in the level EV is given as delta. So this is dEV given as delta. So it is simply 1 over q delta, and this change is happening over this length. So L minus 0, that is L. So delta over L. So the electric field developed is given by delta over QL. So this is quite simple, and the answer for the electric field developed is delta over QL. Okay, so with this ends the problems that I was supposed to solve, and now I would like to say thank you again for joining for this session, and I hope to see you again in the next live session, that is on the Friday 19th August at 6 p.m. Indian Standard Time. So I hope to see you in the fourth live session there. As I have told you in the previous sessions as well, there is this NPTEL course link where you can go and check out the discussion sessions. There you can create a thread so that people can answer your question. Mostly the current years, regular years from the course will answer. Also professor can reply, and if some of the questions are related to these live sessions, then I can also reply there. Also an self promotion is that these live sessions are recorded and these will be uploaded to my YouTube channel. The link for those is given, so you can go to youtube.com/Samadhan Kamble. So in that playlist, NPTEL-ISD playlist, you can watch all these recorded live sessions. If you are if you could not join because of any reason, you can always go there and see the live sessions recordings. And yes, thank you so much again for joining. Have a nice weekend. Thank you.
Thank you, sir.
Thank you. You're welcome. Okay, so thank you so much again everyone for joining for this live session. I hope to see you all in the next live session, that is for the week 4 on Friday, August 19th at 6 p.m. Indian Standard Time. Meanwhile, you can go and check out this NPTEL course link where uh, you can ask questions on the discussion forum, and also these recordings which are for these live sessions will be uploaded on my YouTube channel, so you can go and check those recordings in case you could not join because of any reason. And yes, so thank you so much again for joining, and have a nice weekend.